Yeah, good morning, and thank you very much. It's a great pleasure for me to present this results to you today. I really like to thank the organizers for inviting me. I understand my topic is a little bit off the mainstream, but I think chosen on purpose. And for me, it has also been so far a really interesting conference, and I like the presentations and the discussions very much. So I'm going to speak about laser excitation of a nucleus. We have chosen this title with the idea to appeal to a broad audience of physicists from nuclear physics. The application side that we would like to address is, I could have added to the title, maybe work directed towards a nuclear clock. So oh no, I need your help again.
This one needs to be the other screen. Well, try again. Sound. So then it's this one after this one. Good. All tested, all working, and then of course, no, nothing was anymore. That's not exciting. Try again.
Yeah,
I think so.
Okay, thank you. Yeah, I'd like to introduce the team. It was a cooperative work of two teams. My team at PTB in the time and frequency department, and then we worked together very closely over many years with the team of Thorsten Schumm in Technical University Vienna. The experiments I'm going to present today were actually done in Braunschweig, but with very important input of materials and methods and equipment from Vienna, and a number of the Vienna people commuted to Braunschweig frequently. So nice cooperation that we had there. I'd like to introduce the subject a little bit with an citation from an eminent physicist and from about 100 years ago, in this case, Albert Einstein. In 1925, he was traveling Latin America, and he was invited by the Argentinian Academy of Sciences, admitted as an honorary member. And during this meeting, they had a Q&A session, and that was reported in this report of the Academy. And somebody asked the question, is it possible to obtain induced radioactivity by bombardment of matter with quanta of light? And then in looking at the answer of Einstein, one sees that he was surprised by the question, maybe not really prepared. So he is saying different considerations. Probably it exists. The difficulty of the observation, such a phenomenon, if it exists, the effect which has to be observed is very small. But finally, he concludes, yeah, there should be a confirmation of this effect. Hard, but possible. Okay, well, that's a nice statement and maybe motivation. And so I'd like to start a little bit to point out analogies and differences in the interaction of light with atoms and molecules, with which we are familiar, I think most of us here in this room, and on the other hand, nuclei. So atoms are composed of two signs of charge, positive and negative. Nuclei have carrying only one sign of charge, and this makes a little bit of a difference in terms of induced electric dipole moments. Atoms are bound by a central force which determines the symmetry of the states, of the eigenstates, and the selection rules for transitions between the states. Inside the nucleus, we have non-central forces. So the simplest composite nuclear systems, the deuteron, already has an electric quadrupole moment, which you would not expect for the symmetric bound state of a proton and a neutron. So the forces are considerably more complicated. In terms of scaling of the transition rates, we need to consider these quantities here. So of course, some scaling for magnetic transitions go with the magnetic moment. So this is the Bohr magneton for the electron. The nucleus, of course, can also have a magnetic moment, but the scale here is 1,800 times smaller than the Bohr magneton, just the mass ratio of proton to electron. And for the electric transitions, there is the scaling with the size of the multipole of the charge distribution. So if lambda is the wavelengths that we are interested in, and r the size of the system. So for optical light and atoms, this is already a small ratio, like 10 to the minus 4. But for the nucleus, the magnetic dipole, for example, the lowest convenient order that appears in many nuclear and atomic processes, scales with the square of the magnetic moment. So you can see it would be suppressed by about 6 orders of magnitude. And the electric multipole, it scales with this ratio of antenna size over wavelengths to the power 2L, where L is the multipole moment. So already for the dipole, this is a small number, and for higher order multipoles, it becomes even much smaller. So the nucleus, in fact, is a very badly matched antenna for the long wavelengths of light. And this was maybe, I don't know specifically if this was what Einstein had in mind for this quick question, but it illustrates why the interaction of radiation with the nuclei is suppressed or is much weaker than what we know from atomic and molecular transitions. So why is it interesting? Why are we interested anyway? And yeah, so I'm coming from the institute, from the time and frequency department. So our task to build clocks. So in fact, the motivation here is to build a clock. And we speak about the transition from the atomic to the nuclear clock. So I should briefly explain what I mean. So this is a generic setup of the of an optical atomic clock. There is a laser as the oscillator, and the laser is driving a resonance in a quantum mechanical two-level system that determines the transition frequency. There is a servo loop that keeps the laser in resonance, the laser frequency in resonance with the atomic system, so to universally define the frequency, and then a clockwork can be added in order to produce a standard frequency or time scale. And what we are interested in is to replace this now atomic or molecular two-level system with a nuclear system. So we want to drive a radiative transition inside the nucleus instead of driving a transition of a valence electron in the electron shell, like it is the case in all the atomic clocks we know today. And such a procedure promises 3 advantages. So a higher accuracy, a higher stability, and high sensitivity to new physics. This is the high or additional sensitivity because it is not a pure electromagnetic system that we are looking on, but it is also, of course, influenced and determined by the strong interactions in nuclear forces. And I'm going to explain a little bit more the first 2 aspects. Why should this nuclear clock be more accurate and more stable? So we are going to look, we are primarily interested in the nuclear resonance, but we will not look at a bare nucleus, but we will look at a nucleus inside an electron shell. And it means that we can choose a clever combination of the electronic quantum numbers, of the symmetries of the electronic state. And this allows us to find ideal conditions for the interrogation of the nuclear transition, in a sense that the nuclear transition becomes independent of external electric and magnetic fields to a degree that is not obtainable with an individual electronic transition. And this is a bit technical, but I'm giving you here the 2 main examples that are known today. So it depends on the symmetry, on the quantum numbers of the electron state. So our first proposal like 20 years ago was to be pointed out that it would be possible with states of low electronic angular momentum, 0 or 1/2, depending on whether the nuclear spin is integer or half integer. And a bit later, the group of Alex Kuzmic, Andrei Derevianko, they found a bit more general class of states, so-called stretch states, where these are states of extreme angular momentum, so where the nucleus and the electronic angular momentum are aligned, and they have the same properties of suppressing the field-induced shifts. And this is an important class of the shifts that today are determining the uncertainty, the systematic uncertainty of the advanced optical clocks that are studied. The other aspect is the high stability, and this is really again a dramatic change that one can envisage in a nuclear system, because we know the optical clocks with trapped ions, they work with a single ion or with maybe 5 ions. Lattice clocks work maybe with a few 10,000 or maybe a million atoms. But here we can work in a solid state environment and solid state density, because the nuclear transition will not be broadened significantly by the lattice. And this is, of course, something that is known and that has been exploited in nuclear physics for a long time in Mössbauer spectroscopy. But here, the nuclear clock, it promises to do something laser Mössbauer spectroscopy, so driving a Mössbauer transition in a solid with a coherent laser source. That's been considered by us, by the Vienna team, by UCLA. So, and of course, the promise to go to like 10 to the 10, 10 to the 15 nuclei. And in fact, this is the systems that has been studied and that I will present today all belong to this class. And then there's another criterion, the domain of nuclear transitions, of course, to go to high frequency, to X-ray frequencies, the clock would be ticking faster. And this would eventually also allow a more higher stability and higher accuracy. But of course, it would require to have a suitable radiation source that is the X-ray laser or so with a narrow line, which that is not available today. A year ago, there was a remarkable experiment published on a 12 keV transition in scandium. This was excited with in Hamburg at DAISY with an X-ray free electron laser, but that's of course a high energy installation and not something that is suitable for a laboratory clock. I have on the slide already here the little diagram showing the nucleus of interest. So we are interested not in this high energy, but in the low energy range. And here the system of interest is the thorium-229 nucleus. It is shown here in this graph. This summarizes the excitation energies of the first nuclear excited state as a function of proton number. So on a logarithmic scale, and you can see the scale here is keV. So most of the first excited states are in the 10 to 100 or 1,000 keV scale. And then there is this one exception on the logarithmic scale here, the far outlier, the thorium-229 at 8 eV. Then there is one uranium at about 80 eV, but it's not really suitable for excitation. And this is the scandium X-ray transition that I just talked about. So for now, I'm going to focus on this thorium system, which is the nucleus that we are studying. This is giving an overview of the nuclear level scheme of this nucleus. If you come from atomic or molecular physics, you may think, oh wow, this looks exactly like a molecule. It is rotational bands. But then you look at the energy scale here, okay, hundreds of keV, okay, that's not a molecule, it's a nucleus. But the structure can be very well understood in terms of rotational excitations. But then we are interested in this very low energy here. And this is two band heads of rotational bands, the ground state, and then this is the first excited rotational band, but the band head is nearly at 0 energy. Here it's written 4 electron volt, what later turned out to be about 8 electron volt. So that is the transition that we are interested in, the lowest known transition in terms of nuclear excitation energy. So in order to the information on the transition wavelengths was from gamma spectroscopy, so it had a huge uncertainty. It was decreasing over the years, but still, when we started the final search experiment, it was still like a tenth of an electron volt, or about half a nanometer. So in order to drive it with a laser, we had to build a widely tunable laser system, and at this rather challenging, still for laser technology, challenging wavelengths of about 8 electron volt. So we decided to do it in 4-wave mixing. That's a technique that was well established already in the 1990s. So we use xenon gas. We are driving ultraviolet photons close to a 2-photon resonance in the xenon at about 10 electron volts. So these are photons at 250 nanometers. And then we are creating a polarizability in the gas, and then we are mixing here with an infrared photon. And the difference frequency then of these 3 photons is then emitted as tunable and coherent VUV radiation. And yeah, xenon is a suitable medium for this type of frequency of UV generation, and other people had done it before, and we decided it was a suitable system for this task. So a bit more in detail on the system. Of course, to drive this 4-wave mixing in the gas, one needs high intensities. It's so we working with pulsed dye amplifiers that produce nanosecond pulses of like tens of millijoules energy. But since we needed a good control on the frequency, we start with 2 CW seed lasers. And these are then amplified and to produce the high intensity for the nonlinear process. Both are in the infrared. One is at 750 nanometers. We generate a third harmonic to produce at 250 nanometers, driving the 2-photon. Then the other one is the infrared. And then it's just focused into a xenon gas cell. One has to choose the proper pressure and alignment of these beams in order to get the phase matching. And then one can produce microjoule pulses at the VUV radiation. Then one has to continue to work under vacuum, under very clean conditions, and then can go to an ion trap or to any kind of other spectroscopy setup. In order to first characterize the system, we worked on electronic transitions in trapped thorium ion. So indeed, we used an ion trap. Thorium plus is known to have a very rich electronic level structure. And so we were although these levels were not listed in the literature, nobody has looked at this energy range in this ion before, but we were quite sure that we would find resonances. And indeed, it is the case. Within like 1 resonance per day or so, with a little bit of search, and we found new levels. We could submit these to the NIST database, but our main motivation here was to characterize the tunability and the spectral property of this laser source. And you can see here the fluorescent signal from this excited state. And then we can see also with 2 photons, we are already doing resonantly enhanced ionization, producing thorium 2+. It also stays trapped in the trap, so we can, on another transition with another laser, detect the buildup of the 2+ ions and the depletion of the 1+ population. But as I mentioned, the main motivation here was to characterize the laser. You can see the line widths here of about 10 gigahertz. Yeah, we checked, of course, these electronic transitions. They are strongly saturation broadened with these microjoule energies, but extrapolating back here, we noticed lowest line widths of about 6 gigahertz. But then we looked at the numbers. So we were successfully driving this electronic transition, but I told you it's much harder to drive a nuclear transition. And so we calculated, so what would be the excitation rate of this laser trying to drive the nuclear? And the expected excitation rate was disappointingly low, like 10 to the minus 7 per second per particle. And if you imagine we doing an experiment with maybe 1,000 particles or so, it would be a very difficult search experiment. So we decided at that stage that we should switch to a different system and work closely with the Vienna team that we had been cooperating already before, because over the years they had succeeded in growing calcium fluoride of optical quality doped with 10 to the 14, 15, 16 of the thorium 229 nuclei. And it's a transparent crystal. Here it's illuminated with a blue laser. It's a few cubic millimeters. And so the idea here is to use this VUV radiation that we produce and then drives the nuclear system. And the nuclear system would be embedded in the crystal. And it would be, the transition would happen within the band gap. We would mainly hope to interact with the thorium directly, not much limited by absorption or other electronic processes in the calcium fluoride. That was why the calcium fluoride was chosen. Here's what's known about the structure of this solid. So the thorium exists as a 4+ ion. This is rare gas like symmetric electronic structure. It replaces one of the calcium 2+. And then for charge compensation, so to compensate the extra 2 positive charges of the thorium, 2 fluoride interstitials have to be integrated, and that's the structure as it is known from structure calculations. So this experiment box was then mounted at the laser beamline in Braunschweig. Here a bit more the details. I explained to you the laser system already. So this is now the crystal support and detection box. So the crystal is mounted on a cold finger, cooled with liquid nitrogen in order to avoid damages in the crystal. And then the fluorescence is collected with a huge mirror. Fluorescence light is spectrally filtered via 2 dielectric mirrors and then focused on a VUV sensitive photomultiplier. The experimental sequence is very simple because we were expecting the lifetime of the excited state like to be several minutes. So we can excite with the fixed laser frequency, we just excite the crystal for a few minutes and we switch the laser off. And in the dark, we watch for the decay of the resonance fluorescence signal. We also installed a CCD camera here, which is just sensitive to the visible, and it's turned out to be very helpful for alignment. So if you pass the VUV beam through the crystal, we can see some laser-induced visible light also that shows that the laser is there. Okay, so this was the experiment. It was ready in the beginning of last year, and then we underwent some search for like nearly a year. This was the previous uncertainty from the nuclear physics experiment. It was done at CERN, and it had about a 0.4 nanometer uncertainty range. And this is all the data points, each one like an hour or so of data taking over that we took over the year. You see, we went for more than 1 sigma in order to be sure not to miss a point. And then towards the end of last year, we saw in like a year, about a 4 sigma initial signal within the 1 sigma uncertainty of the range. And then within a few hours or so, we were able to improve this, to optimize the signal and to show that it was really a significant signal. I am now showing here the spectra we obtained after a few days of optimization. So we are scanning the laser here over the nuclear resonance, and one can see in the raw data a characteristic asymmetric line shape. So the red points here scanning from low to high frequencies, and we see a relatively sharp rise and then a slow decrease of the frequency. And this is just due very simply to the fact that we are hitting a very narrow line, a millihertz wide line, with a gigahertz wide laser. So the slow decay that we are seeing here is just the radiative decay of the excited population. So and knowing that this interpretation is right, one sees immediately when inverting the scan direction, scanning from high to low, one sees the same type of symmetry, but in the mirror image. And then so for this effect, of course, it can easily be corrected. And then after applying this correction, the 2 line shapes nicely overlap and have a common resonance frequency. And then after seeing this first signal, we spent like another month or so of doing control experiments. And this is because seeing such a weak signal, and that's something that nobody has observed before, of course, one needs to make sure not to be fooled by some parasitic processes, and there may be long-lived defects in the solids, or there may be electronic long-lived states also. And so we did a number of experiments. Crucial experiment was to use a crystal doped with a different isotopes, the long-lived thorium-232, which has, of course, the same electronic structure, which all the chemistry steps in the preparation of the crystals were the same. But the nuclear structure, of course, it would be completely different. And indeed, at a much lower rate here, we see no signal at all. So this was quite convincing to us that indeed what we see here is a nuclear resonance. And yeah, then later, after further optimization, we obtained a bit nicer line shapes. We checked different crystals, different concentrations. We checked that the lines are at the same frequency. This is here a factor 3 or so in concentration. We see a factor 3 in intensity also. So we see a linear scaling, no saturation of this, and the line shape and the line width determined by the laser with a bit more than 10 gigahertz spectral width. The spectrum that we are seeing here, as I mentioned, determined by the laser. Inside this line, one would expect a spectrum to look like this. And this is a line splitting. This is due to the interaction of the nuclear quadrupole moment. The charge contribution of the nucleus is not complete, it's not spherical, symmetric, it has a quadrupole moment, and the quadrupole moment interacts with the electric field gradients inside the crystal. So calcium fluoride, a ionic crystal, positive and negative charges sitting very, very close to each other. So there's a very strong electric field gradient inside, and this would lead to a quadrupole splitting that here we could not resolve, but it has been resolved in the meantime in a different experiment. And then quite soon following us, we heard results from a group at UCLA in the US, group of Eric Hudson, and they had also been investigating this system for a long time, but with a different host crystal. So they had, differently from the Vienna team, they had not chosen calcium fluoride, but lysef. It's also a wide bandgap crystal. They had doped this with thorium developed these crystals, and then they had a similar laser system like ours, also with a 10 gigahertz line width, and they found exactly to the gigahertz resolution here exactly the same transition frequency, and that's of course again an indication that this must be a nuclear process. Any electronic doping or so would sensitively depend on the host crystal. Changing the host crystal would shift an electronic line on the terahertz scale or so. Again, this was a clear indication that a nuclear process. This shows a little bit the history of the uncertainty of this energy determination. So the blue points here are the one from the pre-laser age, gamma spectroscopy. You can see the huge uncertainties, and then here the about factor more than 1,000 improvement with the first laser excitations. A good agreement between these two experiments with the different hosts, calcium fluoride and lysef. And now, more recently, maybe last week, if you have followed the news, there has been a third experiment that has worked now with the same calcium fluoride crystal from Vienna, but with a different type of laser system. That's a group of Junier at Gila in Boulder. And they are producing the VUV as harmonic generation from a frequency comb. The frequency comb operating in the infrared, being stabilized there. All the parameters of the comb stabilized to an atomic clock, so that the individual comb lines here could be tuned with the maybe kilohertz or so level precision in the VUV. And then the individual lines, of course, are much narrower than the 4-wave mixing laser that we had. But they, of course, benefited from our number selecting down narrowing the search range to like the 10 gigahertz, so they could then do the fine tuning in this range. And within a few weeks or so of searching, they found the resonance. And you can see the number here. Now they are giving it with an uncertainty of 2 kilohertz. So again, nearly a factor million improvement in the, so over like half a year, the uncertainty of this transition frequency has now decreased by more than 1 billion. And I think this really opens the field to precision laser spectroscopy. And they were also able in this, you can read it in this paper, to resolve this quadrupole structure, which contains interesting information. Switching back to our experiment, so what we could control and measure precisely is the radiative lifetime. So that's a simple experiment that we are doing for the spectroscopy. We are exciting for some time. We switch off the laser and then we watch for the decay of the fluorescence in the dark. This is raw data. Here's the blue point, and the orange curve is just a simple single exponential fit. And you can see it's a very nice agreement. Again, it was something that was important for us because there are sometimes parasitic processes, long-lived luminescence processes where charge separation may happen in electronic degrees in the crystal, but then one finds diffusion processes and they are never exponential. So here it's really a nice clean exponential. We checked several aspects. That the decay constant here, 630 seconds, is identical for differently dopings, for different chemical preparations, and also independent of the temperature. So we started the experiments at liquid nitrogen temperature, and then we became more courageous in terms of damaging the crystal, going up to above room temperature, and the lifetime is independent. So we see some indications here that what we observe really is a robust nuclear process. That's what you expect from a nuclear process. You don't expect the wavelengths to be shifted by the host crystal. You don't expect the decay time to be determined by the crystal or by temperature or other effects. In order to make contact with nuclear theory, there is an interesting aspect. Also, I think that's related or maybe interesting for the quantum optics community. So we are observing the decay, the spontaneous decay inside the dielectric medium. And this has been discussed early on already. Here, there's a nice paper by Gerani, who's from the 1970s, showing that the magnetic dipole spontaneous transition rate will be enhanced inside the medium by the third power of the refractive index. And the refractive index in the ultraviolet is important. So this is a factor of 4 or so. And it is an effect that is actually hard to test in an electronic system, because changing the index usually also changes the environment. Here we could not yet really test it, but so we applied this correction for the index, and then we can calculate the half-life for the isolated nucleus. It's about 1,700 seconds. And now we can compare to nuclear theory. One can compare to so-called Weisskopf units. You may not know about these. This is just dimensionless nuclear oscillation strength. And what nuclear structure had predicted had a relatively wide uncertainty, about an order of magnitude, but our value was well within. And now over the past year, there have been a number of data available. So I'm plotting all the experimental data that have been now reported, and scaling here with the n to the third power. And you can see that, yeah, it is still a wide range, but the lifetimes here, this is our calcium fluoride work. There's been a work with trapped ions, and the isolated ions, observing the decay with a huge uncertainty, but it seems to be consistent. And then results from other crystals are a little bit outside. So I think we have a good understanding, I think, of the decay rate, and I think, yeah, it will be interesting to get more feedback from nuclear theory. What can they learn from the data that we are measuring on the nuclear structure? So we were happy to get this published end of April in First Reflector. We had they gave us the cover page with the artist impression here of the crystal of the thorium inside the calcium fluoride. So that was the story of the first experiment. So of course, question what is next? There is, I think, 2 obvious and important steps to increase the spectral resolution to build a narrowband VUV laser system. The system that we have designed was really and used was really meant for the initial search. Now we have a much higher accuracy in the target frequency, and now we can start to design a frequency stable laser system. It is technically a challenge because it has to be in the vacuum ultraviolet spectral range. What the GILA group has done is harmonic generation is certainly one way to go, starting with an infrared femtosecond frequency comb, and then doing harmonic generation. In the harmonic generation, the line widths originally in the infrared will increase due to mixing of all these modes. So it's not really clear what kind of line widths can be obtained. So far, what they have observed is 300 kilohertz. Of course, we would like to go towards the millihertz or so natural line width limit, or maybe 1 hertz would be great. And so we are now considering if it could also be possible with a CW laser. And then the other exciting direction is, of course, what I mentioned initially, to go to the trapped ions. So the crystal, very interesting, of course, because of the strong signal with the many nuclei. But of course, we would like to switch back to go to the trapped ions, driving the transition there. The advantage will be that the control of the systematic shifts will be superior with the ions. One does not have to worry about these crystal fields, which may be temperature dependent and depending on pressure on the crystal. So the high precision version of the clock will likely be with trapped ions, and that's the next experimental step that we want to undertake. So we are actually working on preparing this. So for the trapped ions, so how would we detect the weak nuclear excitation? We would not simply look at the fluorescence like we did in the crystal, but exciting, we could look in an individual ion. Exciting the nucleus inside the ion would lead to a change of the nuclear spin and to a change of the hyperfine structure. So this can be non-destructively and very efficiently read out via electronic spectroscopy. And in this way, I think we should be able to detect with high probability a single excitation of a single ion. And that's how we hope to bridge these like 15 orders of magnitude in particle number from the solid state system to the ion system. This is a spectrum that an experiment that we did together with a group of Peter Tirolf in Munich, where the isomer was produced in a recoil experiment. This is electronic spectroscopy of thorium-2+. You can see strong hyperfine components of the nuclear ground state, and then here these were lines of the isomer, and this was the first experiment where we could actually determine nuclear moments and so of the isomer. The charge state of choice for the excitation will be the 3+ ion. It has a simple electronic level scheme. It can be laser cooled. We did some initial experiments on this, and now this is here now closer to cold atoms. So this is thorium-229 3+ ions, sympathetically laser cooled with strontium+. You can see the E over M ratio of the two ions is similar. So they are closely coupled inside a radio frequency trap. Here the fluorescence pictures are taken with the fluorescence light of the strontium+. So this is a pure strontium class Coulomb crystals, and then we start to inject the 3+, and they show up as dark regions here. The higher charge means that each ion suppresses a bit more, repelling several strontiums and leading to a larger dark volume here. This is about 10 ions in a linear string inside, and this is maybe 20, 30 or so thorium-2+ ions. And these are now at a millikelvin temperature and ideally prepared for high resolution spectroscopy. So this would be next steps in the experiment, but I think it's really opening a field for investigation. I think there will be quite some interesting nuclear physics to be studied here. There will be material science studied in these Mössbauer systems, and the clock is, of course, in terms of applications, maybe the most interesting and the most promising applications. But I think there is more to this field, and I think now the doors are open, and for more investigations, and we are quite excited and to see what's going to happen. One may speak, the terms actually, it's not coined by us. People have been talking about quantum nucleonics. You think about quantum electronics, quantum photonics here, quantum control of a nucleus. And then, of course, quite interesting, I think the fundamental tests comparing clocks of electromagnetic character with clocks, with a nuclear clock, where a strong interaction plays a role. Very promising to look for violations of the Einstein equivalence principle, possible time dependence of the fundamental coupling constants. People have suggested using it as a detector for dark matter, if some dilaton dark matter would couple to hadronic matter. Again, I think from the point of view of ideas and proposals, the field is open. If you look on the archive now, there is proposals coming up. So it's quite a dynamic field. So yeah, it was my pleasure today to introduce this to you. Please stay tuned, and I'd like to close in thanking the team again and our funding, which mainly comes from an ERC Synergy grant. Thank you very much for your attention, and I'm looking forward to answering questions.
Thank you very much for the presentation. There are questions. Marcus.
Hi, Ekkehard. Great science. So I was wondering, one trivial question and different questions. Anyway, first one, saturation intensity was how high?
Sorry?
The saturation intensity is, can you tell us this already? So the line width is very narrow, so hypothetically you would expect that you need only very little power because the line is very small, but on the other hand, it's a magnetic dipole. Do you know what the...
It just scales with the, I don't have the number in my mind, but it just only scales with the line width. So it's millihertz. No, I can only tell you a fantastic number. It will be very, very low. But
so it's broadened already by the light that you shine in.
Yeah, we are not now. We are not saturating. So we are basically doing. So we are illuminating with a gigahertz broad light, but the nuclei are only absorbing like maybe natural line with millihertz. There is some we expect some broadening in the crystal, which is maybe on the 100 hertz scale. But so the so for the CW laser system. We are target power could be a nanowatt or so, and focusing a nanowatt to a square millimeter should be in the range of saturating, or at least inducing Rabi oscillation.
And in order to avoid the crystal field effects in calcium fluoride, can you implant it also in solid helium to make it softer, so to say?
I think you know more about. I looked at it briefly. Yeah, I think the band gaps are promising. I think the band gaps of the rare earths of the rare gas solids should be transparent. But maybe the structure is not well enough understood, and also I think I would worry a little bit. So we have like nanogram or microgram of radioactive substance available, and so one would need to be very careful in how to prepare and handle this crystal. Again, I think I'd like to discuss with you. You know, it could be an idea. Some people have thought about this already, but I don't know about any specific experimental effort.
And okay, for the same reason, probably a fountain configuration also is no option, because you would waste too much of this material. Huh?
Sorry, what?
A fountain configuration, a beam is kind of too consuming, so to say.
Likely, yeah. So we have like a microgram available in the lab, so we prefer to store it in the trap or in the crystal.
Further questions? So maybe one question. connected to that, is it conceivable to do like cooling, trapping, atom interferometry with thorium? I mean, it would be the element to do quantum clock experiments.
Yeah, I think there is besides the clocks, there could be interesting quantum dynamics effects, especially in the solid. So one would have very long coherence times, like minutes, very little coupling or perturbations from the environment. Maybe one would have an opportunity to structure the material that is doing something photonic structure in a spatial structure inside a solid. One could store and maybe eventually also process quantum information. But you see, this is all hand waving what I'm saying now. I have no specific idea right now, but I guess there could be opportunities for many applications. Maybe the vacuum ultraviolet laser will be a little bit of a challenge or so, but that's a question of laser development, and I think this field will also contribute to the motivation to develop laser systems in this wavelength range, and maybe it could lead also to practical system from other laboratory uses.
All right. There is no further question. Let's thank Ekkehard again. Next talk is given by Gabriel Müller from Leibniz University of Hanover.